I need your attention up here. We're starting the second half of 6.5. 6.5, operations with radicals. So here we are still simplifying like we did yesterday. But along with that, we are also adding, subtracting, multiplying, and dividing radical expressions. So it's not just given one expression, one term, and asked to simplify. You might have an operation that you need to do before you simplify. So for this first set of examples, it says you can use the product and quotient properties that we covered yesterday to multiply and divide some radicals. So I have two examples of radical expressions that require multiplication. So when you see expressions like this, we're going to look at A together. You first have to make sure, in order to multiply these together, the index of each radical has to be the same. So notice these are both square roots. What that means is whatever is in the square roots, we can multiply those together. If the index on each of these was different, we could not actually multiply them. So there are multiple ways to work through these. You could simplify each radical first and then multiply. I find it easier to multiply them together first and then just simplify the one radical in the end. So if I were to multiply these, I can multiply the 6 and the 4 that are outside of the square roots together. So that would be 24. And then I can multiply everything that's in the square roots together. So I have 8 times 2, so I now have the square root of 16. I can multiply the c cubed and the c, and that becomes c to the 4th, add the exponents. And then I can multiply the d to the 5th and d to the 3rd, and that is d to the 8th. Again, add the exponents. And then once you've multiplied, I now just have one square root. I would then simplify that like we did yesterday. So I'm going to still have the 24. I'm going to break this into the square root of 16, the square root of c to the 4th, the square root of d to the 8th. And so I have 24 times square root of 16. It's a perfect square. Square root is 4. So the 24 and the 4 will be multiplied together. Square root of c to the 4th, c squared. Do we need absolute value bars? No, because it is an even root of an even exponent, but it's an even exponent in the end. And then square root of d to the 8th, d to the 4th. Yeah, so that's actually a nice square root. It's a perfect square, all of the pieces. And I don't need absolute value bars in the d either. So I just need to multiply 24 and 4. That's 96. So 96c squared d to the 4th. All right, so then for part B, I'd like you to answer in your groups, and then I'll walk around and check, answer questions. Careful with B. You have a 2 4th roots, so they're not square roots when you're simplifying, they are 4th roots, but simplify after you multiply like we did yesterday.
Well, I'm not really either, but I kind of been forced to watch them. So. I'm just waiting till you follow me. Hey, I told you right away. Yeah, I didn't. I heard it over there. I didn't want to tell her because I didn't.
All right. Here, double check what you have. I know some of you at the beginning, you weren't quite done. I do need your attention up here though, please. So make sure this, I know this is a common mistake I see, and I don't want to see you make this mistake as we move forward. When you're rewriting any radicals, students often forget the index that was originally there. So some of you I know started writing square roots, and that's going to give you a completely different answer, and it's wrong if that's what you had. So make sure that you are paying attention to whatever index is there. That means you're taking the fourth root of everything. And then you do need absolute value bars around the y, because it was an even power, or even root of an even power, and the ending power on y is odd. Okay, so make sure that if you haven't been practicing and you're making those little mistakes, that's why the practice is good, just to have you watch for those small details that are there. They're important details. All right, next set of examples. We can add radical expressions, add and subtract. These are added and subtracted in the same manner as monomials. It's very similar to combining like terms. That's how I usually refer to it, combining like terms. So in order to add or subtract radicals, The radicals, like it says, must be like terms, and what that means is they are like radical expressions if both the index and the radicand are identical. So if the index and then what is inside the radical they have to be the exact same. So for example, if you had, it gives 3 examples here. If you have the square root of 3b and then 4 times the square root of 3b, these are like radicals because they are both square roots and they both have 3b inside of the square root. So those are like radicals. These two are unlike because while they both have 3b inside of the radicals, one is a square root, one is a cube root. So you could not combine these. You could not add or subtract them. These are also unlike because even though they're both square roots, one of them is the square root of 2b, the other is the square root of 3b. So the only way you are allowed to combine them is if they are the same. So for the two that are like up here, if you have the square root of 3b and there is an invisible 1 in front, and then you have the 4 times the square root of 3b, you would combine the coefficients in front, the 1 and the 4, to get 5, and then you would keep the square root of 3b. So that would be those two radicals combined if we added them together. Or we could subtract them, do 1 minus 4, get negative 3 square root of 3b. So it would be like adding 1x and 4x together, or subtracting 1x minus 4x. So in example 2, here in both parts we are adding or subtracting radicals. So if we look at a together, we have 5 square root 12 plus 2 square root 27 minus square root 28. So all of the radicals are square roots, but right now what's inside of each radical, 12, 27, 128, those are not the same. So we cannot add or subtract any of those together as they are. What you can do though is anytime you have a radical in an expression, you need to make sure it's simplified. So we should look at all 3 of these square roots and see if we can simplify them, and then if any of them end up being like radicals or like terms, we can combine them. So I'm going to start with the 12. I know I can't take the square root of 12, but is there a perfect square that goes into 12? 4. So I could split the 12 into the square root of 4 times the square root of 3. And the square root of 4 is 2. So it's 2 square root 3. So then overall for this term, because I had that 5 in front, the 5 would get multiplied by that 2. So this term would become 10 square root 3. Okay, now that term is simplified. I can then do the same thing to the middle term if there's a perfect square that goes into 27. So can I split 27? 9 and 3. So square root of 9, square root of 3. Square root of 9 is 3. So it's 3 square root 3. And then because of the 2 that's multiplied in front, I can multiply the 2 by this 3. So that would be 6 square root 3, and that term was being added. And then for the square root of 128, I'm going to bring down the minus sign right away. But the square root of 128, is there a perfect square that goes into 128? 4 and 32, but Grace had the largest. 64 goes into it. 64 times 2. So remember, if you don't pick the largest perfect square, or if you did 4 and 32, you could still simplify the square root of 32. So square root of 64 is 8. So I have 8 square root 2, and there wasn't anything in front, or there was just a 1. So this is just minus 8 square root 2. And then once you have all of your radicals simplified, I can't simplify square root of 3 or square root of 2. Notice I do have 2 terms that have the square root of 3. So those terms are like terms. This is similar to being 10x plus 6x, so I can combine the 10 and the 6. The square root of 3 doesn't change. So this becomes 16 square root 3. And then because the 8 square root 2 is not a like term, I would just keep that in my answer, minus 8 square root 2, and this would be the fully simplified expression. So simplify all of the radicals in the expression. If any of them are like radicals, you can combine the terms, the coefficients. Otherwise, you still need to make sure all of the radicals are simplified. So go ahead and answer part B, simplify 4 square root 8 plus 30 square root 50. And then we'll check it. All right, double check in case you weren't done when I walked around. 23 square root 2. So a couple things to make sure of is when you're simplifying the radical, make sure that if there was originally a coefficient, that you are multiplying that coefficient still with that term, and then only combining them if they are the same radical. And the radical itself, the square root of 2 in this case, doesn't change. So then under example 3, so the 2 examples we did for example 1, those were multiplying. Example 3 are also expressions that are being multiplied, but you can see they do look different. So if we look at example A, we have the quantity 6 root 3 minus 5 multiplied by 2 root 5 plus 4 root 2. What process would you guess you would use to multiply these? You had to say, I think this is how I would multiply them. What does it seem like you might do? FOIL. You use FOIL to multiply expressions like these. Or the box method if you prefer the box method over FOILing. So when you just have to be careful with how you're multiplying. You can only multiply numbers if they're both outside of a square root or both inside of a square root. So for example, for this first term, when I multiply 6 root 3 by 2 root 5, The 6 and the 2 get multiplied to be 12. And then because I have the square root of 3 and the square root of 5, I can multiply those to be the square root of 15. Okay, so I multiply the numbers both in front and the numbers that are both inside to get my term. So that's the first term. The outer term, 6 root 3 times 4 root 2. 6 times 4 would be a positive 24. Square root of 3 times square root of 2 is square root of 6. And then my inside terms, negative 5 times 2 root 5. So the negative 5 doesn't have a radical, so I can multiply the negative 5 with the 2 in front to be negative 10. And then I still just have the square root of 5 attached to it. And then my last terms, minus 5 times 4 root 2, I can multiply the minus 5 by the 4 to be minus 20. And then I still have the square root of 2 attached to it. Okay? Once you are here, once you have FOILs, then you now have an expression like we saw in both A and B in example 2. You have terms being added and subtracted. You can only add and subtract them if they are the same radical. Since we have the square root of 15, 6, 5, and 2, none of those are the same. Check if you can simplify any of them. Is there a perfect square that goes into 15? I see some no's. I mean, 1 goes into 15, but 1 goes into everything. Otherwise, 15 is 5 times 3, and those aren't perfect squares. So the first term is already as simplified as it can be. Is there a perfect square that goes into 6? No. 6 is 6 times 1 or 2 times 3. 1 is the only perfect square. This is as simplified as you can get it. Can you simplify the square root of 5? Some no's. Square root of 2? No, all of these are already simplified. None of them are the same. So this is your answer. This is the simplest form. It doesn't look like it because it's 4 terms, but you can't combine or simplify any of those terms. Okay, so I would like you to multiply the expression in part B. Multiply and simplify. They can be tricky. All right. So this one, double check. It should just be 71. Now, I have one example. I know there's two examples on the back. One for sure I'd like to go through with you. But these two expressions in the parentheses, they have a special relationship. Notice in the two parentheses, the 7 square root 2's are the same and the 3 square root 3's are the same. The only difference, one of them is minus, one of them is plus. These are called conjugates. You heard that term before in chapter 4 with imaginary numbers. Complex conjugates when we had a plus b times I and a minus b times I. So conjugates, that process of multiplying conjugates is also used with radicals. So when you multiply expressions that are conjugates, their product should always be an integer. All of your square roots, all of your radicals cancel out. So that means on the back, that's what's explained on the top. Binomials of the form, so if you have a square root b plus c square root d, and then a square root b minus c square root d, where a, b, c, and d are rational numbers, these are called conjugates of each other. And this is another way we can rationalize denominators. If you have a radical expression that looks like this, one of these in your denominator of a fraction, then you would multiply by the conjugate in order to get rid of that square root in the denominator or to rationalize that denominator. And that, again, is because, like you just saw, when you multiply conjugates, the square roots cancel out. It's equal to an integer. So in example 4, we have this number here, 2 over the square root of 5 minus 1 is a special number. Maybe it was brought up when you were in geometry, but golden rectangles have been used by artists and architects to create beautiful designs. Many golden rectangles appear in the Parthenon in Athens, Greece. The ratio of the lengths of the sides of a golden rectangle is this number. So it is a special number or a number that's well known for the golden rectangle reason. But it says use a conjugate. What we're going to do is use a conjugate to rationalize the denominator in order to simplify this. This is not simplified because of the square root in the denominator. So I'm just going to rewrite the number we have, 2 over the square root of 5 minus 1. And so just like yesterday, when you have a square root in the denominator, you need to multiply by something in order to get rid of the square root in the denominator. So this expression is different because it's a square root added or subtracted to another quantity. So when you have this case, you want to multiply by the conjugate of this, and the conjugate would just be changing, in this case, the minus to a plus. So the conjugate would be multiplying by the square root of 5 plus 1. And then I have to multiply by that same quantity on the top. Okay, so on the top, because I just have a 2 multiplied by that quantity, I just have to distribute the 2 to the square root of 5 plus 1. Careful here, 2 times the square root of 5 does not become the square root of 10, because the 2 is not in a square root and the 5 is. So 2 times the square root of 5 is just 2 square root 5. And then I have plus 2 times 1 is 2. And then when I multiply the denominator, I use FOIL. So I have the square root of 5 times the square root of 5. That's the square root of 25. And then for the outer term, square root of 5 times 1 would be plus the square root of 5. Inside terms, negative 1 times the square root of 5 is minus the square root of 5. And then a negative 1 times a positive 1 becomes minus 1. And so what should happen in the denominator is all of your square roots should be able to cancel out somehow. So the positive root 5, negative root 5, the middle terms cancel. And the square root of 25, that's a perfect square, that's just 5. So your denominator just becomes 5 minus 1, which is 4. On top, I still have 2 square root 5 plus 2. I can't add those together, the 2's, because they're not like terms. But then what I can do from here is, because both terms on the top, the 2 in front of the square root, this 2 and this 4, those can all be divided by 2, so I should divide them by 2 to simplify. So the 2's on the top become 1's, the 4 in the denominator becomes a 2. So simplified, this number is the square root of 5 plus 1 over 2. Okay, any questions on that? So multiplying by the conjugate and then simplifying using processes we've used. What I'd like to do it is a little more challenging of an example because you have more variables with the A's. I would like you, while I walk around and pass out the assignment, and I'll check this example too, I'd like you to look at example 5 and work through it. So it says, in a square with side A, the ratio of a side to the difference between the diagonal and a side is, and then it's this ratio, A over A times the square root of 2 minus A. And it says, use a conjugate to rationalize the denominator and simplify that expression. So again, it's a little more challenging of an example, but I'd like you to work through that, and I'll walk around, I can check, answer questions, but I'll also pass out the assignments. give you a hint while you're working through it too. When it's fully simplified, all of the A's should be gone. There will be no A's in your answer when it's fully simplified.